Bismillahirrahmanirrahim, starting with the name of Allah. So, this is our presentation. We will study about the optical properties of molybdenum disulfide MoS2 thin films. My name is Hammad Shaukat and I am presenting this presentation with my group member Khatija Nawaz under the supervision of Dr. Junaid Ali. So here is the layout. First of all, we'll present the introduction. In introduction, we'll discuss about the low dimensional systems, then density of states, then we will discuss about the energy band gap, surface to volume ratio, quantum confinement effect, graphene, molybdenum disulfide, MoS2. Then we will move on towards the growth of MoS2. In that we will discuss about the temperature mapping, RC cleaning, and then we will go towards the thermal vaporization of MoO3 precursor first, and then we will do the sulfurization of MoO3 precursor. Okay, and at least we will do some characterization like optical characterizations of our growth film, and then last we will discuss about the summary and future work. Okay, so here is the low dimensional system based on the dimension of the materials. So first of all we have the natural occurring materials that are 3D materials in which all dimensions are greater than 100 nanometer, and these materials are called as the bulk materials. Now moving towards the two-dimensional system. In two-dimensional system, we have 2D systems, 1D systems, and 0D materials. Okay, 2D systems in which at least one dimension is less than 100 nanometer, like quantum sheets, nanosheets, and in 1D at least two dimensions are less than 100 nanometer, like nanowires. And in 0D, we will discuss about the in which all dimensions are less than 100 nanometers, and these they are called as the quantum dots. Okay, so let's move towards the next, density of states. In density of states also changes as we move from high dimension to low dimension, as you can see from this figure. Like in 3D you can see the variation of density of state having a continuous variation with respect to energy. So density of state have a continuous behavior in 3D systems. Okay, while in 2D you can see that at specific energy the density of state has a constant behavior. You can see the density of state is constant at this some energy, and at this energy again constant. So in this 2D materials, the density of state is constant at specific discrete values of energies. Okay, and in one dimensional you can see this is a distribution function. Okay, distribution function. And in 0D, which is a quantum dot, you can see this is a discrete behavior. Okay, here you can see the material is now electron is now more localized, and you can say in a specific energy level. The electron is only a specific energy level. You can see from this delta function peak. Okay, there is less degree of freedom in 0D, but there are more degree of freedoms in 3 dimensions. So density of states also changes as we move from high dimension to low dimension. So the energy band gap next. So energy band gap also got increased when we move from high dimension to low dimension. So you can see that this is your 3D bulk material. You can see there is a small band gap between. Band gap is basically the band gap between the valence and the conduction band. So bulk materials has low band gap. As you move from low dimension means 2D, 1D, 0D, like quantum dots, you can see this is a quantum dot of 6 nanometer. So but this is large in size. So you can see this has larger band gap energy. Okay. Band gap energy also depends upon the size of the quantum dot. So as you can see, this quantum dot has larger size. Okay, 6 nanometer, and this is for 4 nanometer, and this is for 2 nanometer. The smaller the quantum dot, the greater is the energy band gap. Why the band gap got increased? Because once your material is in zero dimension means quantum dot, the wave function of electron and hole overlaps, and this creates the energy difference. So if the energy difference, so that's why the band gap got increased. So the conclusion is band gap also increased as we move from high dimension to low dimension. Next, move on towards the surface to volume ratio. So surface to volume ratio also got increased as we move from high dimension to low dimension. As you can see that the surface to volume ratio is inversely proportional to the characteristic size. You can see at this 3D this bulk material which is larger in size, so means it has low surface to volume ratio. As you can cut, like let's suppose you can cut this block from center. Now it becomes 2D because more surfaces are taking part in the reaction. That's why, okay. So more the faces taking part in the reaction, so you can say it has more surface area. Okay, so as you can move from high dimension to low dimension means you are breaking the material in nanometers. Okay, the surface area got increased. As you can see for this, the surface to volume ratio is 6. So this is a quantum dot. Okay, so as you move from 3D to 0D, you can see that the surface to volume ratio got increased. Okay, now move towards the quantum confinement effect. Degree of freedom also got increased as you move from 3 dimension to 0 dimension. Like in 3 dimensions, your electrons have availability to move in all 3 dimensions x, y, z. So if they move in all 3 dimensions, it means they have no confinement, zero confinement. And in 2 dimension, you can see now your electron will move in the only two direction like x or y, but there is confinement in 1 dimension like z. So in 2 dimension the confinement is now 1. Okay, and in 1 dimension your electron will move only in 1 dimension. Other 2 dimensions are confined, the electron cannot move because the dimension of that 2 dimensions are less than 100 nanometer. Okay, and last, in 0D your electron is confined, they cannot move in any dimension. That's why the quantum confinement is uh, 3, because now confinement in all 3 dimensions xyz. You can see this for bulk material xyz, they can move in all the 3 dimensions. Here the electron can move in only in x and y, here electron move in only x dimension, and here your electron is now got confined. Okay, now move on towards the graphene. There are some properties of graphene. Graphene is basically the best studied 2D material. It has freestanding atomic layer of carbon. It means that you can remove the layer of graphene. Okay, it has high carrier mobility, high current density, high electrical conductivity, high thermal conductivity. So these are basically the applications or features of graphene. And expectational mechanical strength, you can bend those graphene like structures. Okay, and graphene also is nearly transparent, like it only reflect 2.3% of the light. And the main factor which we need is that you can see that the graphene has high surface to volume ratio. So that's very important to use graphenes in making nanostructures. Okay, because more surfaces are take part in the reaction, and these materials are very prominent for the fabrication and characterization in optoelectronic devices. Okay, so the main limitation of graphene is that it has zero band gap. It has no band gap. You can see from its EK diagram that this is your valence band and this is the conduction band, and you can see this is the main point, connection point, and this connection point is so called as the Dirac point. Okay, and there is no band gap. So the limitation of graphene is no band gap. So if this has no band gap, so it can conduct very fast. You can switch on the practical device, but you cannot switch off directly. It will switch off normally, but if you want to switch off any circuit automatically, so it would not happen in graphene because it has no band gap. You can switch on easily but not switch off the devices. Okay, so this is one of the feedback drawback of graphene. So that's why we are moving towards the TMDs, which are new materials. TMDs basically has a formula of general formula of MX3, where M is basically the transition metal and X are the chalcogen atoms. So basically, transition metal is to be sandwiched between the two chalcogen atoms. So you can see these group 4, group 10 are the transition metals. Okay, and these are the chalcogens. Okay, so chalcogen atoms has to be sandwiched. Transition metals has to be sandwiched between the chalcogen atoms. They form TMDs, transition metal dichalcogenides. Okay. So one of the TMD is the molybdenum disulfide MoS2. Okay, you can see here moly atom is sandwiched between the two transition atoms, which is sulfur. So here are some properties of the MoS2, like it has the same graphene-like properties. So that's why we can use it in making the nanomaterials. It has same electrical properties, conductivity, it has excellent mechanical strength like in graphene. But the main important application of MoS2 is that it has tunable energy band gap. Okay, its indirect band gap is 1.2 eV, which is in bulk material, and its direct band gap is 1.8 eV, which is in a monolayer. So as you can see, as we move from 3 dimension, which is bulk, to you can say one dimension monolayer, so you can see the band gap increased. Okay, so its indirect band gap is 1.2, which is in bulk, and its direct band gap is 1.8 ev, which is in monolayer of graphenes. So this is very important because you know that graphene has no band gap. That's why we are using MoS2 instead of graphene, because it has band gap. Okay, it has both direct as well as indirect band gap, means tunable band gap. And the next is the optical properties. So that's why we can use MoS2 in photodetectors and solar cells, and it's two-dimensional material which is strong in bonding and it is weak out of the plane bonding with van der Waals forces. Okay, so you can see this is the EK diagram of the MoS2. Here is the valence band and here is the conduction band. This is basically the monolayer of the graphene, because the band gap you can see indirect band gap is 1.8 ev. Okay. Next, move on the formation of MoS2. How MoS2 form? This is the moly atom, which is sandwiched between the two sulfur atoms, and their bond is covalent bond inside, and their bond length is 0.41 angstrom. And how formation of monolayers? So by end-to-end attachment of the MoS2 molecules form the monolayers of MoS2. Okay, so you can see, and here you can see how bilayers formed. So monolayers up down formed bilayers, and these monolayers connect with each other with van der Waals forces. Okay, and how bulk formed many monolayers up down formed bulk MoS2. Okay, now move towards the flow chart of the growth of the MoS2. So first of all, we will have to do the temperature mapping of the quartz tube. Why? Because we want the temperature inside the quartz, inside the you can say the tube furnace or quartz tube is not uniform. So we must have to measure each 2 centimeter apart to measure the correct temperature, so that we will accordingly put our materials inside the quartz tube. So that's why temperature mapping is very crucial. Next is the cleaning of substrate. We are using the silicon substrate, so we must have to clean the silicon substrate. Okay, and this is very important to clean. We will clarify in upcoming slides. Now the growth of the oxide layer. So we also grow oxide layer on the silicon substrate because we don't want any contaminants on the silicon substrate, so that we are unable to make the best layer monolayer of MoS2. That's why we must have to first grow an oxide layer which not allows any contaminants to put on. Okay, next we have to grow MoS2 film on the silicon substrate. Okay, and for that we will first diffuse MoO3 precursors on our silicon substrate, and then we will do sulfurization process. After sulfurization, you can see the monolayer of MoS2 now deposited on our silicon substrate. Okay, so this is basically the flow chart what we are going to do. So for that we did the temperature mapping, and here is the temperature mapping flow chart. You can see temperature versus distance graph starting from we measured the quartz tube temperature from 0 centimeter up to 78 centimeter inside the quartz tube, and this is the temperature distribution inside the quartz tube, and we got the maximum temperature at nearly somehow before the center at 10, which is 1058 degrees Celsius. Here the temperature is increasing continuously. Here we got maximum temperature, and then we are got the temperature is getting down. So this is the distance versus temperature inside your tube furnace, or you can say inside the quartz tube. So how we can clean the substrate? We are using a method which is RCA cleaning, which is radio cleaning America cleaning. Okay, and this method consists of using three beakers. Basically, we have to do this RC cleaning to remove the contaminants from the glass substrate. So, RC cleaning basically removes organic contaminants, also oxide layers, ionic contaminants, or it can also make passive layer. Okay, passive layer also makes so that no other contaminants come on the silicone substrate. Okay, so that's why this RC cleaning of substrate is very important. So to do RC cleaning, first we need three beakers, and these three beakers cleaned by isopropyl and acetone separately. Okay, and in first beaker we need 50 ml of deionized water and 10 ml of ammonia and 10 ml of hydrogen peroxide H2O2, and we have to mix and heat it 70 to 80 degrees Celsius and only for 10 minutes. Once it's done, you have to move your substrate to the next beaker, and in next beaker you have to take 500 ml of now deionized water, and you have to take 10 ml of hydrofluoric acid HF. Now again you mix the solution for 15 seconds only. Once it's done, you have to move towards the third beaker. In third beaker you have to take now 50 ml of deionized water, which is poured with 10 ml of hydrocarbon, okay, HCl, and you have to take 10 ml of hydrogen peroxide H2O2, and you now again have to heat your substrate around 10 minutes. Okay, once it done, your substrate is now successfully cleaned and a passive layer is formed on your substrate, and now you are surely go for the formation of monolayer of MoS2. Okay, so now move towards the growth of MoS2. So this is the temperature inside the quartz tube. This is our tube furnace, which is the quartz tube containing 21 centimeter outside from both ends. Okay, you can see this is the controller where we control the temperature. Okay, we are and this is the on off button of the tube furnace. So this is the temperature set. We set temperature at 1130 Celsius, and these are the distances inside the quartz tube where at 9 centimeter the distance is less than 130 degrees Celsius. At 62 centimeter temperature is 915, and 63 it is 920. Why we take the temperature mapping? That's why we take the temperature mapping, because we need these specific positions temperature inside the quartz tube, because from literature we know that we have to place our samples of MoO3 precursor, our sulfur and our substrate at those temperatures which we required. So at these temperatures, which we gain after the temperature mapping, here we have a distance 9 centimeter. That's why we placed our sample here, and here the accordingly positions are 62 centimeter and 63 centimeter. Now what we have to do? So positioning of precursor and the sulfur in the ceramic board. So here is you can see our quartz tube, in which contain, here we have to insert our silicone substrate, and here we have to put our MoO3 precursors at this position, and at this position we have to place our sulfur powder in a boat. Okay, and this is our quartz tube, and we have to inlet with the nitrogen gas. Okay, so how it works? Basically, positioning of ceramic boards for thermal vaporization of MoO3. Okay, So basically this is our quartz tube, and this here we placed our sulfur powder. We take these images from articles, okay, and these are sulfur powder placed in both. We have to place at this temperature where the temperature is less than 130 degree. We can place anywhere this sulfur powder below temperature 130 degrees Celsius, and below 130 is between 0 to 2 centimeter position. Okay, you can place anywhere between 0 to 2 centimeter. And we have to place our silicone substrate this at 63 degrees at 920 degrees Celsius and at 63 centimeter position inside the quartz tube. And just after 1 centimeter we have to place MoO3 precursors, okay, and which is at 915 degrees Celsius. So now how it works. So you can see the process of thermal vapor. First we have to do thermal vaporization of MoO3. For that we have to place our boat which containing MoO3 precursors, and here is the silicone substrate. Okay. Now see what happens when we initialize the nitrogen gas. Why nitrogen gas? Because we have to evaporate this MoO3 on the silicone substrate, and we are very careful about that. We cannot too much increase the pressure of the nitrogen gas that the molecules drop here, and pressure should not also be very less that it can drop here. We are very precise that the molecules of MoO3 precursors drop on this silicone substrate. So you can see once nitrogen gas is formed, so you can see MoO3 molecules now going on your silicone substrate. Once all the MoO3 precursor is successfully placed on your silicone substrate, the next step is the sulfurization. So here is the sulfurization. For sulfurization, what you have to do, you have to put your quartz tube 17 centimeter inward. Why? Because now we have to evaporate the silicone, and silicone is not evaporate at 130 degrees Celsius. So we must have to go from literature. We know that silicone evaporate maybe at 280 or 240 degrees Celsius. So that's why we, from our calculations of temperature mapping, we know that if we move our quartz tube 17 centimeter inward, we got new positions and new temperature for this and this new temperature positions. You can see this is how quartz tube going inward 17 centimeter, and now you can see these are the new positions. Now your sulfur powder is at 26 centimeter, which is correct temperature at 240. Now this is the good temperature at which your sulfur powder evaporates. Why we not only push the sulfur boat, why we push the whole quartz tube? Because we also make the reaction, we also want the reaction of MoO3 precursor with the sulfur. They both react with each other and they form MoS2 layer, and at previous temperature which is 920, your chemical reaction would not start. Your chemical reaction would also start if the temperature is greater than 1000 degrees Celsius. From literature we know that. So that's why we moved the whole quartz tube. That's why your this board got temperature greater than 1000, and this board got the at 240 at which your sulfur powder evaporates. Okay, so you can see, so new position is 80 centimeter here. So this sulfurization process, how it works. So this is your one board at which your MoO3 containing silicone substrate is placed, and here is your sulfur powder. Okay, both containing, and here is the nitrogen gas inlet we have to put to gain the this nitrogen gas is basically not basically this is not an inert gas. Nitrogen gas is inert gas at some specific temperatures. At this temperature this is not inert gas. This would not react with the sulfur as well as MoO3. This will not disturb our reaction. This will only give a push of the molecule. That's why we are using N2. We are not using argon gas, because argon gas is you can say inert gas. It would take a reaction with these molecules. So monolayer cannot make find. That's why we are using nitrogen gas, because this is not inert and it would only push your molecules. So now see how your sulfur powder move and go to the silicon MO3 containing precursor. So here your powder is moving and here placed in on your, once all your sulfur powder have moved, you can see your monolayer of MoS2 film now made on your silicon substrate. Okay, so this is the procedure. Now these are basically the parameters which we must have to take to this process. Oxidizing layer contain 122 minutes, vaporization of MO3 take 15 minutes, sulfurization process take 25 minutes. These are basically the parameters of doing best layer of MoS2 monolayer on your silicon substrate, and these parameters from literature. Okay, so you can see these are data growth temperature parameters and quality of precursors and flow rate. Okay, nitrogen gas flow rate, and here is the distance of the substrate and the MO3 which we take. Now move on to our characterizations. We did first of all the optical microscope of MoS2 crystal. So you can see the triangular like shapes formed because the structure of MoS2 is hexagonal crystal. Okay, that's why the optical images like you can see these triangular like shapes. You can see here. You can see here many triangular like shapes means that here continuous monolayers formed. Here you can also see triangular like shapes means continuous monolayer film here produced. And this is 20 micrometer zoom, and this is at high temperature. You can see 800 degrees Celsius. You can see how, so from optical images we can see how sharp our monolayer formed, what is the crystal structure, mm, what is the layer. So it also tells us about the layer. So you can see here is light color basically refers as monolayer, and here this dark yellow color basically shows the bilayer form here. Okay, and this dark shade basically shows the here the substrate. Okay, and here you can see on this side continuous monolayer formed, also bilayer formed here, and here you can see substrate containing less monolayers. So by these optical images we can easily clarify where our monolayer formed and where not, and what is the crystal structure of our MoS2. And we can also, you can see a small dot inside your triangle. So what is this? This is basically the monolayer of MoS2. Okay, so these basically sometimes happen at high temperature. You can see these images at high temperatures at 800 degrees Celsius and 800 degrees Celsius. You can see the flakes containing center dot. These center dot basically shows that the nanoparticle located, means here monolayer formed at the center. As you move from center to any other side, you can see monolayer now form to bilayer or any other layer. Okay, so at the center your nanoparticle formed. Okay, so you can also see these small dots. Here you can see small dot less, some but less. Why? Because you can see the temperature is now less than 800. So high temperature is also very crucial for the monolayer of the MoS2. Okay, so here the temperature is, you can see, 725 degrees Celsius, less temperature. So that's why we cannot clarify a center dot. And here somewhere we can find, because this is some high temperature, 750. Okay, so this is basically the optical microscope results. We can clarify the uniformity, how uniform our MoS2 layer is formed, how thickness, how thick our layer is, means monolayer, bilayer, multi layers. So by thickness we can clarify these steps, or we can also measure the crystal size and density. So crystal size can be measured by a tool which is in Windows like ImageJ. ImageJ is basically a tool which you can find the size of your crystal. Okay. Now move on towards our next characterization, which is the SEM, simple electron microscope characterization of MoS2. Okay, so from this characterization you can also visualize the morphology. Okay, morphology, like you can again see the triangular like shapes of MoS2. So SEM also clarifies your morphology of of your sample, and it also clarifies the thickness. We can easily clarify the thickness, like where monolayers, where bilayer, and where multilayers is formed. As you can see from this figure, this light shaded part is basically the monolayer, and this dark black basically shows the bilayer. So by SEM we can easily clarify where monolayer and bilayer form, and this white is basically the substrate. Okay, and these SEM images also reveals the surface roughness. We can see the roughness, how plain our surface is, how rough our surface is, how porous our surface is. So we can conclude these results from by SEM. As you can see from this figure, how porous your surface is of MoS2 growth, and this is 100 nanometers zone. Means these are nanoparticles formed. Okay, MoS2 dots formed, quantum dots formed. These are quantum dots, you can say, because the dimension is here is 100 nanometers. Okay, we can see how rough the surface is, and we can also see that how porous our surface is. Here we can see the surface area is larger, because this is nanoparticle, so definitely the surface area must be larger. Okay, so from these we can also identify the surface area, and you know that surface area, getting information about the surface area is very crucial for the nanoparticles. Okay, because for nanoparticles surface area is more, your surface area is more, so you are in high dimension. Okay, not in nanoparticle. So basically this is the SEM image of MoO3 precursor. When we only evaporate our MoO3 precursor on our silicon substrate, so this SEM image is basically shows, and these are the SEM images of MoS2 precursor. Okay, so we can easily clarify how sharp our crystal is. Okay, so this basically shows, and we can also measure the size, as I mentioned before, by using a software like ImageJ. How well defined, how smooth your structure is, can this information be get by SEM. And our last characterization is basically the atomic force microscopy, AFM. Basically, AFM shows the topology of your image, basically topology of your crystal. Topology means 3D structure. So by AFM you can easily clarify the height of your growth. How? So you can see this is the 3D image of your MoO3 film. Okay, 3D image. So basically AFM contains a cantilever tip. Basically this cantilever works on the principle of attraction or repulsion. This cantilever has to move on your whole monolayer. Okay, and when there is depth, your cantilever moves down, and when there is height, so cantilever moves up due to repulsion, and when there is downside, so it is attract. So cantilever moves according to the principle of repulsion and attraction. It uses a cantilever, and there is a laser beam which is fall on the cantilever, because cantilever has to be moved up and down, and laser is also reflect to a detector, and they detect the pulse of the laser, and they make this pulse like graph, and this graph basically shows the confirms the height If we have bilayer, so definitely this is heighted, so it shows this this value. So as you can see, these are the AFM images of MoS2 film after sulfurization. And as I mentioned you before, this center dot is basically the nanoparticle monolayer, okay, nanoparticle form, 100 nanometer dimension. And definitely, if this is nanoparticles, so here they show after taking FAFM, they show less depth. So as you can see from this, as you move from here, here the peak is high. This is nanometer. In y-axis, basically nanometer. So 16 nanometer is greater or 4 nanometer is greater? Yes, our 4 nanometer is greater. Okay. So as you can see from this, as you are moving from this, the graph is starting from here. You can see small peak, 4 nanometer, which is a larger value than 16 nanometer. It basically shows that here is some bilayer, means more height, more height of the layer, means multi layers here. And as you move inward to the center of the crystal, you can see the graph is going upward to the, and maximum is at the center, and it is at 15 nanometer, you can say. And 15 nanometer is a small value than 4 nanometer, means here your a thin layer is formed, means monolayer is formed. At the edges, it's bilayer, multilayer form, and at the center is monolayer form. So by this can be concluded by AFM. That's why we are doing AFM to check the thickness where monolayer, bilayer form. Okay, and this is again, this is your MoS2 film, and this is your silicon substrate. So this value basically shows the height peak, basically, which shows that monolayer formed here, and similarly here inside shows height peak. Okay, so that's about the AFM images. Okay, we can see the 3D image. We can also make 3D image like this. We can see 3D image. We can measure the height of our crystal made, okay, nanoparticle which is made. So these all things can be revealed by doing AFM characterization. Okay, so that's all. And the last is the summary. Basically, we grow MoS2 film on our silicon substrate by using chemical vapor deposition, and we do optical images, which we see the triangular like shapes, and we see the SEM images of the MoS2, which basically shows how sharp, how porous, how rough, and about tells us about the surface area of our nanoparticle growth. And at last, basically, the AFM, which basically tells us about the height or topology of our crystal growth. In future work, basically, we can improve our the growth of MoS2 uniformly by using new techniques, okay, like to diffuse MoO3 precursors on the silicon substrate uniform, so that we make our growth of monolayer of MoS2 uniform growth. And we can use future work should be that we can use this mono growth of MoS2 in practical applications like in electronic devices, or you can say the diodes or transistors. And thank you. We appreciate your time and attention, and we are grateful for your time and grateful for the opportunity to present our work. And we welcome if any question or feedback. Thank you.